Okay, so now what we want to do is apply the principles of the kinetic theory of gases to a gas. So here's a question. What is the average speed of an oxygen molecule at room temperature? So in the air around you is lots and lots of oxygen molecules. And every one of those molecules is moving around the room at a certain average speed. Now sometimes they go faster than that speed, and sometimes they go slower than that speed. But what would be the average speed of the air molecules in the room around you right now? So first we're going to write down what you're given and what you're looking for. So the room temperature is, let's say, around 70 degrees, and so 20 degrees Celsius, but that's the wrong unit. We need to use Kelvin, so that's going to be 273 Kelvin. And we also are going to need to know the mass of an oxygen molecule. And so that turns out to be that number there, 5.31 times 10 to the negative 26th kilograms. Okay, now we need to select the formula that's going to connect the letters. So we need something that has a T in it, something that has an M in it, and then something that says something that has the velocity in it. And so we have just found out that the average kinetic energy of a molecule, so 1/2 mv squared, so that's the average kinetic energy of a molecule, is going to be related to its temperature by 3/2 kT. So now we're going to plug in the mass. We're going to plug in the temperature. We know what the K is, so the K is going to be the Boltzmann constant. So we're going to plug all of those numbers into the formula, and then we need to solve it for the letter V. And so we're going to need to take a square root to get to that V. And it turns out to be 477 meters per second. Now remember, 1 meter is this big. And a football field is about 100 meters. So those air molecules that are whizzing around your head right now are going on average 477 meters per second. Well, if that's true, why aren't you being knocked around by all of those molecules? Well, remember, they have a very, very small mass. So that means that even though they're hitting your head and bouncing off of it, they don't have a lot of momentum. So they're not going to be jostling your head very much. Okay, let's continue on here and say what happens to the molecular motion as the temperature drops to absolute zero. Now you already know the answer to this, but now this is going to make more sense. So as the temperature over here goes to zero, then 3/2 times 0 is 0, K times 0 is 0, so this whole thing is 0. And then if you divide it by 1/2, it's 0. Divide by m, it's 0. So now you've got v squared is equal to 0. And then if you take the square root of 0, you get 0. So this means that as you approach absolute 0 Kelvin, then molecular motion stops. Things will slow down. They get slower and slower and slower until finally all of these atoms are basically resting on top of each other, and you don't have any more molecular motion. Now remember that on the atomic level, the atoms would still continue to be able to spin, or the protons in the nucleus would be spinning, the neutrons would be spinning, the electrons would be in orbit, the electrons would be spinning. So nothing's going to go wrong as far as the atoms are concerned. But from a molecular point of view, they would stop moving when this happens. Okay, so let's do a little bit of a summary here about pushers in different kinds of systems and how they're related to energy. So that in lesson number 6, we learned what a force was. A force is a push or a pull. And then we had an equation for work, W, which said that a force multiplied by a distance was the amount of energy it would take in order to move the object. So force times distance is going to be a type of energy, and it was going to be work. So the transfer of energy through the organized motion of molecules was going to be called work. And that's what's going to, so a force pushes a solid. Okay, a torque, T, so a torque was a twist. So if you got a ketchup bottle and you want to take the top of it, you have to twist the top. So a twist is a torque. And it turns out that it's going to take a certain energy in order to twist something. And so the energy it's going to take is going to be torque, T, multiplied by the angle through which you rotate it. So the more times you twist it, the more energy it's going to take in order to do that. Then when we talked about fluids, we referred to, with the fluid, we applied a pressure P on something that could flow, a fluid. Could be a gas, could be a liquid. And so the energy, the work necessary in order to move a fluid through a volume V is going to be P times V, the pressure multiplied by the volume. So force is the pusher of solids. Torque is going to be the pusher, in quotation marks, of a solid when we want it to rotate. Pressure is going to be the pusher of a fluid. And now look at temperature. So we've been talking about temperature T, and it is going to be the pusher of heat. So if this object over here is hotter, has a higher temperature, then this object over here, heat is going to flow in that direction. So you can think of temperature as being a pusher, and it's going to be pushing heat. And so we just have learned that the energy of heat is proportional to the temperature. So if you increase the temperature, you increase the amount of energy that you give a system. And then the last one is in electrical systems. In electrical systems, it's voltage. So voltage is given by a V, but did you notice it's a different looking V? So it's this kind of V when I talk about voltages. And so voltage is going to be the pusher in electrical systems, and it pushes electrical charges. So if you've got a wire, and then you take the wire and you attach both ends of the wire to a battery, then electrical charges are going to flow in the wire. So the voltage is going to be the pusher of electricity, and there's energy associated with electricity. And so if you take the voltage and you multiply it by the number of charges that are flowing in the wire, then that's the energy it would take in order to push all of that. So I just wanted you to see that energy is the unifying theme in physics. So no matter what kind of system you're talking about, whether it's a solid system, a fluid system, an electrical system, a thermal system, that the energy is going to be associated with each of these different kinds of systems. Okay, let's do another application of kinetic theory in our next segment.